In my opinion, the biggest challenge we face now is the time scale for testing. And I can liken this to, let's say, composting. Composting already has standards that are developed by ASTM ISO, where we're looking at how long does it take for a plastic to break down in these compost environments. And you can imagine that when looking at disintegration, biodegradation, these tests can run up to 6 months. Now that already in itself might seem like a long time, but when we move to something like soil, we're talking about persistence that's being tracked over 2 years. So since these tests are so long, you'd never want to just formulate and wait that entire 2 years before you can collect data and get an idea on if your formulation makes sense. That's where a lot of new approaches are being done now. Even our group is thinking of ways to accelerate the ways in which we can collect this data, change formulations, and be more agile as we're trying to tackle these more appropriate environments for products such as agricultural ones that we do expect to break down in these soil environments. So in question 1, I know I said one of the main barriers was how long it takes to collect that data, and our group has actually done work to address this. One way in which I'll share that we're tackling this is coming up with predictive models, especially as we talk about polymer blends. So our group is very materials agnostic, meaning that we are trying to tackle specific formulations that have a variety of components in them that are designed for these accelerated end of life. And before we even go into the development of those formulations and start testing them, we actually have a library of data that we've collected internally. There's external data out there that's being shared, and all of that's being used prior to develop these predictive models on which formulations are likely to even show these accelerated biodegradation trends. That's one of the ways that we're tackling this issue of these long-term tests, by really narrowing down and honing in on the best formulations that already have a predicted or expected behavior that we're targeting. So one thing I will touch on that is interesting that we found as we were going through the data that we were collecting, there is an assumption that certain environments are much more challenging for plastics to break down in. So if you think about, let's say, a compost environment, you might say plastics are definitely easier to break down in that versus something, let's say, like a home compost or low temperature compost environment. Even compared to those compost setups, you might say it's much harder for something to break down in soil. It's much harder for something to break down in aqueous environments, and maybe even most challenging in marine. I think we all hear these stories about what's the most difficult environment to break down in and which ones are the most challenging. And this does hold true for a lot of cases where you might look at a single material and see how it behaves in all these environments and say, yes, it can compost, it can soil biodegrade, but it will not break down in water. One of the things that we've seen actually is when we get into blends, you start to see a lot of different behavior now. In fact, one environment that might be seen as more difficult to break down in shows faster signs of biodegradation than something like a compost pile, or even something that might be considered easier to pass than something like a soil or marine environment. One of my hopes, I think, is after the talk that a lot of people are going to be expanding their acceptance and horizon into these biodegradable plastics. A lot of work typically has been done in the food space industry, where we're talking about diverting food waste to compost streams. And I want to see kind of the same trend now as we're talking about these plastics that already end up in these environments such as soil, and thinking about how do we take those same principles, that same chemistry, that same idea of complete microbial utilization of these plastics that can be turned into CO2, and which products is this appropriate for? During my talk, I'm sure I'm going to be covering a lot of different classes, but I'm hoping that the attendees will also reach out to companies like ours and say, have you thought of these products? We would like to work with you and see how your material might not only match performance, but also confirm that we can still tackle those end of life and close the loop on a lot of these agricultural products.